Welcome to Calculus and Vectors exam review for Unit 7 on vectors. This is the part of the course where we change directions entirely and we drop calculus, no more derivatives, and we start talking about this whole other idea called vectors. But this is another whole important part of mathematics. You know, there's two main disciplines or courses that you look at, especially early on in university mathematics. One of them is calculus and the other one is linear algebra, and calculus is obviously calculus and vectors is linear algebra. So you're seeing a little bit of both. We do a bit more vector calculus than we do vectors, but we see some of the really important notation and operations that are required for vectors, dot product, cross product, which we'll talk about here, all that important stuff. And then in Unit 8 we get into lines and planes and doing a little bit of work with those as well. So let's dive into this. Again, there will be this is a lot more recent for us, but there'll be a few little reminders of some of the different things that you can watch out for and a little bit of practice for us. So this first question is a great one for our understanding of what a vector is. Write each of the following in terms of u and v. So if u is AB, then when I label that on the graph from A to B, okay, in that direction is vector u. So that's my vector u, which means E to D is also vector u. And this is what we have a hard time, because people say, but that one's way up there and this one's way down here. So sure, they're the same length, but they're not the same. But that's the difference about vectors, is vectors don't exist in a particular position. So those are exactly the same vector because they have the same direction and the same length, which we also call magnitude. Okay? And then vector v is AF, so it's going this direction, and that's vector v. And can you find another one in this diagram that's the same as vector v? It's this one. So this is also vector v. If you're doing a question like this and you can label these on there, that can be really helpful. By the way, this is not negative v. And that's what everybody wants to do. So they think they're adding v and then they're subtracting v. But that would be the zero vector. Is that actually true? Have you gone, if you go from here to here, have you gone nowhere? No. Look at the distance that you've gone. So whatever that vector is that you've gone, I don't know, but it's not nothing. So this is not negative v. In fact, this is negative v, just going along v, but the other direction is negative v. Okay, and then the other thing is FC is 2AB, so that's F to C, and AB is U, so this is 2U. So again, I can label that on the graph. Now the trick here is now we have to write each of these vectors in terms of u and v. So there's different ways of doing it. You might just kind of wing it and say, well, I'm starting at F and I have to get to B, so I'm going along this one and I'm going along this one. By the way, one of the nice ways of doing this, you could even highlight or something the different ones that you're allowed to travel across. So those are all the ones that I'm allowed to travel across. I'm not allowed to travel there because I don't have an expression for it, and I'm not allowed to travel there because I don't have an expression for it. But another thing you can do is you can split this up. In this case, this is just good review as well. Don't forget, this is FA plus AB, isn't it? And do we have expressions for FA and AB? Well, we have an expression for AB, but we don't for FA, but we do for AF. So as I said, AF is V, so FA is negative V. So you don't have to show this work, but this is what we're doing. This is actually negative AF, which is the same as FA, plus AB, and AF is V. So this one is negative V plus U, or U minus V. Okay, and that's how you could do it. But if you could get to that in one step, that's fine. Generally speaking, these are 1-mark questions. And I traveled from F to B only along the blue lines. What about A to D? So I'm starting at A and I got to get to D. Well, when I've drawn these lines, it's pretty obvious what you're doing. So from A, I'm going down V to F. So this equals V. So I'm going to do this a different way. I'm not going to write it out in terms of the AF vectors and that kind of thing. I'm just going to use the lines that I've drawn in. So I go down here, which is V, because I'm going this direction, plus I'm going along here, which is positive 2u, because that's the same direction that you're supposed to be going, plus, and I have to get to d, so down here again, which is v again. And since I've labeled them, it's really obvious, which is 2u plus 2v. And if we wanted to, we've talked about this, you can factor and write it out like that if you wanted to. Okay, and the last one is f to d. So if I go from f to d, well, I don't know what's going on with this one. This one's even easier. F to c to d. Those should have been in a different order because this one's trivial now that we've already gone from a to d. We went through this one. But this one is 2u plus v. And I think that's it. Fairly straightforward. When you understand that that A, F, and C, D are the same vectors, and A, B, and E, D are the same vectors, and you understand that, then this becomes easy. Labeling your diagram can be very, very helpful. Okay, so that's a great question to test our understanding on what a vector is, the visual nature of what a vector actually is, and get us thinking in vectors. But then we have these questions where you're given some actual vectors. So in this case, we're given the definition for 3 vectors. And what we have to do with that is a whole bunch of the different operations. We're going to probably do some dot products, cross products, different kinds of things here. Okay, so let's dive into it. This first one, A, is quite simply, can you do some basic arithmetic with vectors? Okay, so 3 times u, and I'm actually going to do some of this work as we go. I'm not going to sub in, so I'm going to multiply this one by 3. And we got to put it as a vector. -3, 6, 15, minus 4, and then v minus w. So 3 minus -7 is 10. It's 3 plus 7. 4 minus 0 is 4. And -6 minus 1 is going to be -7. Now I got to multiply that one by 4. And you can multiply by -4 and add, or you can multiply by +4 and subtract. Let's do it by -4 and add. So -40, -16, +28. Now I got -3 plus -40, which is -43. 6 minus 16 plus -16 is -10. And 15 plus 28, I believe that is 43. Okay, and that one is done. Now, what about this one? You could do this. You could kind of do this all in one, all together, but I'm going to do it in 2 different parts. Actually, let's do it all together. We can do it all together. You could do just u plus 2v equals, solve that, and then take the magnitude of that. But we can do this all in one step. So this is going to be equal to the magnitude of u. I'm just going to write that part out because we're not using that yet. Plus 2 times v, and 2 times v is 6, 8, -12. Okay, and we're still taking the magnitude of that, which is the magnitude of, adding those together is +5, +10, and -7. And then you have to remember how to take the magnitude of a vector in 3 space. But it's this simple formula that is based off of Pythagorean theorem, and it's maybe a little bit surprising, but it's actually 5 squared plus 10 squared plus -7 squared. And that works out to 174. So root 174. So that is the magnitude of that expression of vectors, u plus 2v. Okay, and that's important. Being able to calculate the magnitude of any vector is an important idea. Next one is dot product, or there's a little bit of work here to do as well, but dot product. Okay, and oh, actually, sorry, there's 2 things here. I didn't notice that. There's a C and there's a D, so we are not doing D yet. We'll save the dot product for next. We're going to do C first. So a unit vector in the opposite direction of u. So if you remember how to do a unit vector, we have to find the magnitude, and then we divide each of the components of the unit of the vector by the magnitude. Okay, so the first thing we have to do is find the magnitude of u. So I'm going to go back up and I'm going to find out what u is. So it's -1, 2, 5. So this is the square root of -1 squared plus 2 squared plus 5 squared, which equals 25 plus 4 plus 1 is root 30. And then to do it in the opposite direction of u, so again I'll write this down here just to make a note of it. U is -1, 2, 5. So if I'm going to go in the opposite direction, I go positive 1 over root 30, then -2 over root 30, then -5 over root 30. And you can't change those numbers. You can't scale it up because then it would no longer be a unit vector. So you got to make sure that you've done everything you need to do before you find the magnitude, and that's always the last step that you do. Okay. Sometimes we can simplify these ahead of time by doing some work with distributed property or that kind of thing, but in this case it's not worth it, but there's nothing we could do anyway, so we're just going to add them. So u plus v, you know what, I'm going to write these out again so that we can refer to them. So u, like I said, is -1. It's already there on the screen. -2 or 2, 5, and v is 3, 4, -6. So if I add them, I get 2, 6, -1, dotted with, subtracting them should be -4, -2, and 11. And how do you do dot product? You just multiply them, multiply the first, multiply the second together of each, and then multiply the third together of each. And generally speaking, you wouldn't show all this work, but it looks like that works out to -31. We've done a lot of work with dot products, so that's probably not something you need a lot of review with right now. Okay, so there was question C and D, and we've got one left. Two vectors orthogonal to both u and v. U and w, which is -7, 0, 1. So how do we find two vectors that are orthogonal to both u and w? And it doesn't say they have to be linearly independent or anything like that. In fact, you wouldn't be able to do that. So that's one of the reasons why it doesn't say that in this case. But be careful of that. Some questions might say two vectors that are not scalar multiples of each other or that are linearly independent. Or some questions might just say two vectors where you can scalar multiple. How do you find a vector that is orthogonal to two vectors? Cross product. And to do this, we write these out and order count. So I did u cross w, so I start with 2, 5, -1, 2 on top, and 0, 1, -7, 0 on bottom. Okay, and I end up with 2 minus 0. 2 times 1 is 2, 0 times 5 is 0, so 2 minus 0 is 2. And -35 minus -1 is -35 plus 1 is -34. And 0 minus -7 times 2, so 0 minus -14, which is 0 plus 14, which is positive 14. Okay, and you can scale this up or scale this down. So there's one, check, and another one could be, how about 1, -17, so I'm dividing each of these by 2, and 7, or -1, positive 17, negative 7. I mean, you could come up with an infinite pretty easily by just, having them go the opposite direction, or scaling them up by doubling them, or in this case I could divide by 2. Okay, so that's our little bit of review. What we mainly did in this unit was talk about what a vector is, and a little bit of work with just basic vectors and those picture kind of things. But then we did a fair bit of work learning about cross product and dot product, and some of the stuff in like unit vectors and magnitude of vectors. And we also did a little bit, which we didn't cover here, some of the other applications of dot product and cross product, some of the other formulas involved where we can find angles between vectors, things like that. So there are a few other things again that we haven't done here, that we did in this unit, and that are good things to review. But that's a general overview of the most important operations, and generally speaking, what a vector is.